we can get started now. Tonight and the next two sessions, we're going to be discussing uh, uh, methods of analyzing data that we haven't looked at so far this semester. There's a giant hole in the number of methods that we have available to us, particularly once we start looking at doing our final projects. We've dealt with we've dealt with situations where we're combining groups or two groups or a number of groups as far as confidence intervals, as far as binomial distributions, as far as probabilities, p-values, percentages. We've dealt with different groups in terms of comparing them according to t-score, a number of standard deviations apart. In other words, hypothesis testing. But there's certain kinds of data that we haven't gotten to. And that is, in one case, this week, we're going to be looking at when we're dealing with two variables, or more variables, in fact, two or more variables, and both of those variables are categorical variables. We've only almost exclusively dealt with different groups of categorical variables, but for which we're analyzing them for numerical averages. So this time we're looking at a situation where we're dealing with strictly categorical variables. And I got a good example of it that we're going to take a look at right now, where we're looking at two variables. One variable is whether a person is HIV positive or not positive, and the other variable is, let's take a look here, whether or not they use IV drugs. So in other words, both of these are categorical variables. Use of IV drugs is a categorical variable with the value either yes or no, right? It has two possible values. HIV status is HIV positive or HIV negative. What's their HIV status? Well, it's either going to be yes or positive yes or negative no. So we're dealing with something kind of new in terms of combinations of variables that we're going to analyze for. Okay, and I'm going to get started here, and I'm going to actually run through an example where we're going to look at a good way to organize categorical variables. Before I go too much further, can you guys see and hear me okay? Okay, most people seem to be okay. Okay, I got a feeling it's probably your system. I think probably you'll be able to get to it in a second. Okay, again, it's recording, so we'll have it available to us when we're done. I'll check that. Just wanted to take a quick look to make sure. Okay, so I'm going to take an example here where we're looking at two categories, drug use and HIV status. Okay, so we take a random sample of 200 patients in a community healthcare facility, and we find that 40 of these patients are HIV positive. Okay, so we know that the prevalence would be 40 out of 200, or in other words, it'd be about 20% in this healthcare facility. Okay, prevalence of HIV, being HIV positive in this healthcare facility is 20%. Okay, so now that we look at that, I'm going to a closer examination. We are going to take a look at the subjects that are HIV positive and examine them and question them about their IV drug use. Okay, so let's see. 50 of the subjects are IV drug users, and 150 have never used IV drugs when we discuss this with them. So now I'm going to organize this information into a table. And that table is going to be crosstabs. It's going to be very similar to what we did with our diagnostic testing, except this time, instead of having, for instance, instead of having our test, our test was positive or our test was negative in our rows, this time I'm going to have the exposure that we're interested in. Usually it's going to be, usually when you're doing this, you're interested in seeing whether or not some exposure has some influence on some outcome either a disease outcome or an improvement, by use of a drug or without the use of a drug, and so on. Except in the case that you're measuring it, it's either going to be the result is going to be a categorical variable as well. So instead of a test result, I'm just going to say uses IV drugs and does not use IV drugs. Okay, so now our possible outcomes are going to be in the columns. Okay, one outcome is that they're HIV positive, and the other outcome is that they're HIV negative. Okay, so I'm going to organize this information. We know that we had 200 people that we surveyed in this group. Okay, and of those 200 people, 40 of them happen to be positive, and 160 of them happen to be negative. Okay, that was just part of the information that we got when we surveyed them. Okay, so now I'm going to go look at this further. So now that, and we saw that 40 out of 200 was going to be our prevalence, 20%. Okay, so now when we look at this on closer examination, it turns out that among the HIV, the group that was HIV positive, 10 of them were IV drug users and 30 of them were not IV drug users. And among the HIV negative portion of this population, 40 of them were IV drug users and 120 of them were not IV drug users. Nothing's changed here. Here's our 50 people, as we discussed before, that use IV drugs. Here's our 150 people that don't use IV drugs. But now we have a better idea of how this population is distributed in terms of which people are drug users, which people are not drug users, and what their HIV status is. Okay, so now let's take a look at a couple of ways that we might evaluate this. One way that we might evaluate this, now notice we can't use analysis of variance here because there's no numerical variable here. There's only categorical variables. Okay, we can't use a confidence interval because, we can use a confidence interval, but not directly on this data right now. So we're kind of stuck with this, right? So let's take a look at a couple of ways that we can analyze this data. One way that we can analyze this data is compare the risk of being HIV positive if you're an IV drug user and compare that to the risk of you being HIV positive if you're not an IV drug user. That's pretty simple to calculate. And the way we're going to calculate that is right here. I'm going to calculate my risk out here. And my risk is going to be equal to, well, out of the 50 people that use IV drugs, 10 of them are HIV positive out of a total of 50 people. So that's 20% of them are HIV positive. So now if I also look at my group that does not use IV drugs, well, my risk is going to be equal to 30 out of 150. Okay, that's also 20%. So if the risk of being HIV positive is the same for IV drug users as it is for people that don't use IV drugs, what would you say about the impact of IV drug use? If this were true, and it's not true, what would you say about the risk of IV drug use if the risk is the same if you use the drug or not? You'd say that there's no association between IV drug use and persons not using IV drugs, right? No association. Well, now let's change things up a little bit. Let's say instead that we found out of the 50 people that use IV drugs that instead 15 of them were HIV positive and 35 of them were HIV negative. And similarly with the people that don't use IV drugs, since this has got to add up to, we had 40 people that were HIV positive. This must have been 25, and this must have been 125. Okay, well, things changed here now, didn't they? Now suddenly, 15 people out of 50 are HIV positive. If among the group that are IV drug users, their risk of being HIV positive is 30%. higher than the prevalence for the entire population as a whole. Okay, how about the people that don't use IV drugs? Well, now 25 out of 150, right? That's 1/6 or 0.167 roughly, right? 16% of them are HIV positive. Their risk of being HIV positive is 16%. Well, there's a fraction that we can develop here called relative risk or risk ratio. I'm going to call it risk ratio for our purposes, okay, because it's a little bit more descriptive. And another name for it could be relative risk. Well, relative risk can be calculated by looking at the ratio between the risk for IV drug users and people that don't use IV drugs. So that's going to be equal to 30% over 16%. And that comes out to number 1.8. So what this is telling us is that you're 1.8 times as likely to be HIV positive. You're almost twice as likely to be HIV positive if you're an IV drug user versus if you're not an IV drug user. Anybody remember what that ratio would have been if we had done it when there was no difference between IV drug the outcome for IV drug users and not IV drug users? What would that ratio be instead? Right, well, not one, not zero. Good idea. You got exactly the right idea, but not exactly zero. Right. I'm just gonna change this back for a moment so you can see that actually happened. 20. Whoops. Oops. Let me hit escape. 20. 20. This would be 40. This would be 120, I guess. Whoa, did I get that right? I still got it wrong, right? Let's see, 40, 160, 20. No, I got what I do. That was 10, I guess. 10 and 30. That's what I got wrong. 10 and 30. And 120, there we go, 20% each, same as the population in general, and the relative risk is equal to 1. Now, there's another way that we can measure this as well. That's called the odds ratio. Okay, now the odds ratio gets a little tricky. In fact, I'm not going to write it in there. I'm going to copy this whole thing over again down here. Okay, except this time I'm going to calculate not a relative risk, but I'm going to calculate something called an odds ratio. These are our odds, and this is going to be our odds ratio. Oops, excuse me. Odds and odds ratio. Okay, so now this time, what are my odds going to be equal to? My odds are calculated differently than my risk. And the way my odds are calculated is I'm going to take the number of people that among the IV drug users, the number of people that are HIV positive, divided by the number of people that are HIV negative. That's equal to 10 out of 40. So your odds of being HIV positive are 1 in 4, 1 to 4. So in other words, not 1 in 4, but 1 to 4. So for every one person that's HIV positive, there's 4 people that are HIV negative in this group. Well, let's do the same thing down here. 30 over 120. For every 30 people out of there are 100 that are HIV positive in this group, there's 120 people that are HIV negative. Similarly, again, our odds ratio is just the odds of being HIV positive if you're an IV drug user divided by the odds if you're not an IV drug user. So again, we wound up with the same situation. Our odds ratio, when there was no difference in the rate or the odds for these two, the odds were 0.25 or 1 to 4 for IV drug users and non-IV drug users, then the odds ratio came out to be 1. When we altered this and made this 15 and 25 and made this 35 and 125, we found our relative risk was 1.8, right? Because the ratio, the risk of being an IV drug user was 0.3 divided by the risk of HIV positive. If you're not an IV drug user, 0.3 over 0.167 came out to be 1.8. Do the same thing down here. I'm going to do the same thing down here. Okay, just going to substitute these numbers. Okay, and I get a similar outcome. Got a higher odds of being HIV positive if you use IV drugs, compared to if you don't use IV drugs. Okay, and the odds ratio was above 1, was a number larger than 1, because you're more likely to be HIV positive if you're an IV drug user. So this really can be summarized kind of this way. I'm going to put a letter into each one of these boxes: B, C, and D. And the totals going across these rows are A. This is going to be A plus B, right? And the total here is going to be C plus D. And you can just see that's how the numbers work out up here. And the total overall is going to be A. Oops. It's going to be A. Oops. Come on. A plus B plus C plus D. Okay. So if we were going to calculate odds, right? Our odds are going to be equal to A over B, and our odds for the non-IV drug users is going to be C over D. So our odds ratio is what's in A over B, right, divided by what's in C over D, right? Another way of writing that same thing is to invert the bottom fraction and multiply it by the top fraction. It's a little trick from algebra that you guys may remember. So instead of A divided by B over C divided by D, you could call it A times D over B times C. Okay, a little bit simpler math than having to worry about the fractions. Okay, so now, similarly, I could do my risk and my relative risk, right? So my risk is going to be equal to A over A plus B, okay, for non-IV drug users, or C over C plus D if you're a non-IV drug user. And my relative risk is going to be equal to just all of this. Whoops. Let me type this carefully. Oops. Over. Oh, I erased it. Well, you know it's going to be A over A plus B. I don't. Let me go ahead and do this so you can get a chance to see it. Over. Okay, and I'm going to take the bottom part. Just like that. That's going to be our relative risk. So when we calculated it here, our relative risk was 1.8 for exactly the same data, and our odds ratio was 2.14. We got somewhat different numbers here. What they do have in common is that since this number is greater than 1, it suggests that the exposure uses IV drugs increases your risk or your odds of being HIV positive. Had this number been less than 1, what would that tell you about the number being less than 1? What would that suggest to you if the exposure comes up with a risk ratio or an odds ratio which is less than 1? It would decrease the risk. Exactly. That would suggest to you that the exposure was protective. So if we were instead looking at, for instance, use of condoms, yes or no, use of condoms, yes or no, then we would expect this to be a negative number. We would expect that to be a protective exposure as opposed to a non-protective exposure. Of course, if we inverted those two and we made non-use of condoms a top line and use of condoms a bottom line, then again, non-use would be our problem exposure. So they'd be greater than one again. Okay, so now anytime I would do this, the perfect situation for me here, since I know that 40 people are HIV positive in this group out of 200, I know my prevalence is 20%. And I know that from when I started, I'm going to put this down here. When I started off with this being 10 out of 40 and 40 right out of 50 altogether, and this being 30 out of and 120 out of 150, right? We know that the prevalence here was equal, the prevalence overall, the overall prevalence is equal to 20%, right? The prevalence if you were an IV drug user was 20%. And the prevalence if you were a non-IV drug user was also 20%. This is what we would expect if there's no association between IV drug use and non and persons that do not use IV drugs. This is our expected outcome. And had we done this, our odds ratio would have been 1 and our relative risk would have been 1. They both would have been 1 if we really got that outcome. Let's assume for a moment that this is really true in this population. The population, 20% prevalence of IV in this population, and as it happens, out of 200 people, 50 are IV drug users, 10 are HIV positive out of that group. So their rate is their prevalence is 20%. Rate that non-IV drug users are HIV positive is 20%, and so on and so forth. Let's say that that's really true in this population overall. The odds of actually getting these numbers when I really go and sample the population are awfully low, even if this were true. Even if these numbers were absolutely true, the odds of me getting exactly 10 and 40 and 30 and 120 are going to be relatively rare. Because sometimes I may get 9 and 41, sometimes I may get 32 and 118, sometimes I may get 27 and 123, and so on and so forth. The odds are going to be not in favor of me getting this exact outcome. So that means that I'm not likely to get exactly, even if there is no association, I'm not likely to get a result of exactly 1 for the odds ratio and exactly 1 for the relative risk. In this case, I got 1.8, almost 2 times as likely. That's encouraging to me, right? And this is 2.14 times as likely according to the odds ratio. So if I got that big a number, I'm encouraged to think that the difference here, the difference between what I actually observed and what I would have expected to observe if there's no difference, I would say, gee, that's very encouraging that I got that big a number. The question is, how do I know what is big enough numbers? Can I just say, well, it's almost double, or this one's double? Can I say that that's enough to say that, I think that there is an association here between whether or not you use IV drugs and HIV positive? Do you guys think that I can rely on just that number being a 2, as big as 2? Is that enough? Right? We need to understand what the probabilities are that we would get that big a number, even when it's really this situation that there is no difference, right? So there's a couple of ways that I can do this. One way that I can do this is I have to, now my expected result for relative risk, what did I say? If there's no difference between in the exposure, what did I say my risk is going to be? What was that going to be? Somebody help me out with that. We just answered the same thing before, right? We said it was 1, right? That's if there's no difference in the risk. The relative risk would be 1. The same thing with the odds ratio. We said the odds ratio would be 1 if there's no difference, if the exposure is not associated with the outcome, HIV positive. So I would expect that to be 1. So what I need here is I need to know how precisely that I know that particular number. I need to be able to prove that it's different than 1. Now, I want you guys to think back to when we were talking about, and you may remember this from the lecture. Hopefully, you guys got a chance to review the lecture before you tuned in now. Let's talk about how can I compare that? How can I be certain within a certain probability, say with 95% certainty, how can I be 95% certain that this 1.8 is really different than that 1 that I would assume that if there's no association? I want to be 95% sure that it's different. What kind of calculation do I need there? We've done it before with averages and probabilities. What calculation is that? I know one of you can come up with it. What do you think you would use there? How about if I ask you to give me a range of numbers, and those numbers represent 95% probability that I like the idea of critical value, but in this case, we have nothing really to compare it to yet, right? But critical value is going to come up soon, right? But in this case, when we're dealing with odds ratio and relative risk, I need a confidence interval. I want a 95% confidence interval for the true relative risk for HIV drug use and outcome, right? So I want to know, let's say that the 95% confidence interval turns out to be 1.2 to 2. Let's see, 1.2 to 2. That'd be 0.6 smaller, 2.4 to 2.4. Okay. In other words, what that would tell me is that, well, I calculated based on this distribution that the relative risk is 1.8, but my confidence interval is 1.2 to 2.4. I'm 95% sure that the true relative risk, not just for this sample of 200 people, but for the entire population, is between 1.2 and 2.4. So therefore, I'm 95% sure it's different than what? Somebody help me out with what it's different than. It's different than 1. Exactly. I can say I need to show that my 95% confidence interval does not include 1. That I can say that I'm 95% sure that the true relative risk is different than 1. And I would do the same thing with the odds ratio. Maybe the odds ratio will come up to be 1.3 to 2.9 or something like that. Right? So in that case, I have the same situation. I can say with 95% certainty that my odds ratio is different than 1. Okay, so I need to calculate not just the relative risk or not just the odds ratio. I also need to calculate a confidence interval. Now, I'm not going to expect you to calculate confidence intervals here because we're going to use software for most of it. You might ask, calculate the relative risk and the odds ratio, but that's very simple, right? That's just simple math, right? The relative risk is going to be 15 over 50 divided by 25 over 150 and so on and so forth with the odds ratio. That's simple. I made that up. The 1.2 and the 2.4 I made up. You would do it as a probability problem, right? Probability here is 0.3, P here is 0.3, P2 here is, was 0.167 and so on and so forth. And you have 2 probabilities. And remember, we did that, did similar problems. But for our purposes, from this point on, we're going to use software to calculate the confidence intervals in this case. Okay, so I made that up just to show you that the real issue here is not just what you calculate as relative risk, but what the relative risk is for what the confidence interval for the relative risk is. So in other words, if I had found the relative risk is equal to 0.85, comma 2.4, we would say, gee, it could be one. I can't say that there's an association between IV drug use and being HIV positive. I can't say that with 95% certainty because it could be one. One is inside of my 95% confidence interval. Okay, so now in a study, you might actually see a report like this. For instance, if you were studying the the level of lead in in children's blood in a population, if you were using numeric variables, you might see that well the level of blood lead level was 4.5 micrograms, right? And the confidence interval was 3.0 to 5.2 micrograms. You'd say, well, our results showed 4.5 micrograms, but our confidence interval is we're 95% sure for the entire population that the real true mean is between these two numbers. Similarly, when we deal with categorical variables, okay, we're going to deal with relative risk and odds ratio. I might tell you the odds of being, except that in that case, we're not talking about the exact numbers of lead in blood. But we're talking about, like, for instance, it might be living in older housing and living in newer housing, right? And being above the threshold for lead poisoning or not above the threshold for lead poisoning, both categorical variables. Well, the odds there might be, I might say, well, you're 2.3 times as likely to have an elevated blood lead level if you live in older housing versus if you live in newer housing. So they might report the relative risk of older house of exposure of being lead poisoned if a child is in older housing. The relative risk is 2.3. In other words, we calculated based on our sample that we're 2.3 times as likely to be lead poisoned if the child lives in older housing, with the confidence interval of, in this case, it have to be a number below this, 1.3 to 4.2, let's say. Okay. Well, we have not just the number that we calculate the increased risk that we're predicting, but we also have a range for the increased risk for the entire population, the true proportion for the entire population. So we want in an abstract for study, you might actually see this reported that way. You might actually see the relative risk was 2.3 with an odds ratio 95% confidence interval of 1.3 to 4.2, or similarly you might see the odds ratio calculated this way, okay, that the odds ratio for this exposure was 1.8, right, with a confidence interval of 1.3 to I don't know 2.4 or something like that. Okay, so that's the way we would use this information. We need this because we don't have any other way to really effectively deal with categorical variables, two categorical variables. I'm going to give you another tool for working with categorical variables, and that's a tool called chi-square. Okay, chi-square takes advantage of the idea that if there's no association, let me back up one moment. When we do a test like this, right, we do something that since I was introducing this concept of how to do this math, we usually start off with something before we actually do the test. And that is we establish a hypothesis, a null hypothesis, and an alternative hypothesis. So when we're looking at categorical variables, we're looking at whether or not this categorical variable has some influence on this categorical variable. So my null hypothesis is that there's no association between IV drug use and HIV status. Well, if that's true, this is what I would expect to get. These are my expected values. If what I said in my null hypothesis were true, these would be my expected values. Now, if I were then to say, well, that's all well and good, but now when I actually go and survey these 200 people, these are the actual outcomes that I get. Okay, this is the actual outcome that I wound up getting. Now, another way for me to look at this, besides the idea of odds ratio and relative risk, is to compare my expected values to my observed values. I'm going to call these observed values. Okay, so now we know that even if this were true in the entire population, even if there was, like there was no association between IV drug use and HIV status, and we would expect if the overall population is 20% HIV positive, we would expect each of these groups to be approximately 20% positive, HIV positive as well. Well, now I get the IV drug users are a bit higher than 20%, and the non-IV drug users are a bit lower than 20%. There's a difference between these two. So I have to recognize that, again, there is, even if this were true, if I were to survey 200 people, the idea that I would get exactly this outcome is unlikely. But the question now becomes, how likely that would it be that I would get this different an outcome from my expected values? Okay, and a simple way for me to actually calculate that is to just to take each one of these corresponding boxes, right? We have that box and this box. They are the correlating boxes. This is uses IV drugs. This is what I would expect to get. This is what I actually got. I'm going to take each one of those boxes and I'm going to say I'm going to calculate. I'm going to say I'm going to look up. I'm going to calculate over here. I'm going to write that over here. Observed minus my expected values. Okay. Well, my expected value was 15. My observed value was 10. So the difference is 5. Okay, I'm going to do the same thing in the next box. My observed value is 25. My expected value was 30. So my observed minus expected, what is it? It's negative 5, right? Okay, so now I'm going to go to this next box. 35 minus 40 is negative 5. Oops. Forgot to hit escape. Oops, negative 5. Okay, this is going to be negative 5. And this is going to be positive 5. 125 minus 120. Okay, observed minus expected. All right, so now if these turn out to be 0, if I was really lucky and it turned out that I got exactly the same numbers as here, I would say, there's no association between these two. So all of these would be 0. So I'm going to take all of these and I'm going to add them up and see how different they are from 0. Well, they turn out to be 0 also, because if we take 5 from here, when we all add it all up, they're always going to add up to 0 because we're just moving the numbers around, aren't we? So I need a way to describe the magnitude of the difference between my observed value and my expected values without them turning into zeros. So as we've done in the past, we do a little bit of a trick here. I'm going to say that this is not, instead of being equal to just the observed value, I'm going to say it's equal to the observed value minus the expected value squared. And that's going to square that number, which means it's going to be positive. So all of the numbers will be positive. So they'll be much larger than I would have anticipated, but they're at least going to be positive. So now to get them back into the range of the size of numbers I'm working with, I'm then going to, once I've turned them into a positive number, I'm going to divide by the expected value. So I get it back down into the range of numbers that I would expect. And I'm going to do that for each one of these boxes. Okay, that's actually a superscript. That's squared, not just multiplied by 2. So let me do that right here. So this is going to be equal to my observed value, which is 25, oops, I'm sorry, 15, minus my expected value, which is, rather than scroll up, I'm just going to write it in. What was it, 20? Maybe I should scroll up, 10, right? Okay, and I'm going to square that. Okay, that's equal to, okay, let's see. Okay, and I'm going to multiply it by itself. It's multiplying it by itself divided by my expected value, which is that 15. Oops, found an error in the formula. What error did I have in that formula? Oh, it worked out though, I think. Okay, let me do it in my head just so I can make sure it's right. That would be 5. The difference would be 5 minus, it'd be 5 squared is 25. Divided by the expected value is 15. 1.67. That turned out right. Okay, so I'm going to do that the same thing for each one of these other boxes. Okay, this is going to be equal to, what's it going to be equal to? It's going to be equal to the observed value minus the expected value, which is 30. That's minus 5 squared, right, is 25 divided by the expected value, which is 25. So that's going to be equal to 1. Okay, I'm going to do the same thing here. 35, my observed value, minus my expected value. 35 minus 40 is negative 5 squared is going to be 25 divided by my expected value, which is 40. 25 divided by 40, I think I made a mistake already, right, guys? Did I make a mistake on that first one? Did I make a mistake on this one, guys? Right? My observed value is 25 minus my expected value is 30. Okay, so that's 5. Square that, that's 25. Divide by my expected value, which is 30. So 25 over 30. Right? I inadvertently put in to the bottom of that my observed value, not my expected value. And then finally, for this last one, is going to be 125 minus 120 is 5 squared is 25 divided by my expected value is 120. 25 divided by 120. Okay, so everybody in agreement with me there? Does that sound right? So what is my total? My total is 3.33. That's my sum of all of these differences worked out this way. Another mistake? Let's see. Okay, I'm going to take a look at this one. This one is going to be, let's see, observed is 15, minus 10 is 5, that's 25, divided by 10 is 2.5. You're absolutely right. I did the same thing there, right? Okay, good. So now I got a number 4.16. Now, the more different my observed values are from my expected values, the more different I expect this number to be from 1, right? Or 0, right? Normally, if they're exactly the same, that would be 0. The sum of all the differences would be 0. So that number, the size of that number, determines how certain I am that there's an association between IV drug use and non-IV drug use. So the bigger this number is, the more different the expected and the observed values are, and the more likely that I can reject my null hypothesis that there's no association. So now I need something to measure that against. And I think I may have something here. If I take a look at this, I see I have something called the chi-square test, chi-square value. Chi-square, this number that I've just determined, this 4.16, miracle, happens to be the same thing I have in my little PDF file that you can play around with later on. That's uploaded to Blackboard. It's the same exercise that we went through just now, basically. Okay, my chi-square value is 4.16. I want that to be a bigger number. The bigger that number is, the more likely that I can reject my null hypothesis without being wrong. Now, unlike our normal distribution, right, or our t distribution, we have here a one-sided distribution. In other words, 0 is down here. The likelihood of 0 is not real great, but it's not 0 either. The likelihood that you would get, this represents a population that is a situation where there's no association between the exposure and the outcome. This, what you would expect here, is you would expect maybe not a 0 chi-square, but you would expect a small chi-square. And the further away that you get, the less likely that you would get that big a chi-square value if there were no association. So if I go all the way down here, okay, the area that's left to the right of my chi-square value, right, that area to the right of my chi-square value, that area represents the probability that I would get that big a number if there were no association. So we're willing to accept a risk that we might say 5% of the time we might say there's no association. Let's say that there is an association, reject our null hypothesis when there is no association. So we want a chi-square value that's so far out here that it only leaves 5% of this curve to the right of it. So, as you can imagine, if we're dealing with values, exposures, say there's two exposures, but there's more than two outcomes. Maybe one out could be HIV positive, another one HIV negative, another one could be undetermined status, another one could be something else, right? AIDS, an AIDS diagnosis, or so on and so forth. Maybe there's more than maybe it's, instead of it being a 2x2 table, the outcome could be a 2x4 table or a 4x2 table. Maybe if we were comparing hair color versus HIV status, we could have red hair, brunettes, blondes, so on and so forth. So we can have many possible values for the categorical variable hair color and two values for outcome. So 4x2, that would be a 4x2 table, right? So, and that would mean that we're adding up more of these boxes. So a larger number may not be more positive proof that there's an association if you have more tables. So somehow more values. So somehow the size of this table has something to do with this what number we should accept. In other words, this distribution is affected by the number of values that we have for our two variables. Okay, so now the way that happens is that we're going to look for degrees of freedom. So now in this case, the way we're going to calculate degrees of freedom is going to be equal to the number of rows minus 1 times the number of columns minus 1. Okay, so how many degrees of freedom do I have here? Opinions? Degrees of freedom? How many degrees of freedom do I have here? 1 degree of freedom. Exactly. So now I need a table that I can look up what my critical value, see, this is the actual chi-square value that I calculated. Chi-square looks kind of like a capital X, Greek letter chi-square, basically a capital X. I can't draw it that well here. But I need to know how big this chi-square value has to be for 1 degree of freedom. That value is going to be my critical value for chi-square. I'll draw it that way. Okay, so naturally, I need a table for that. And in the back of your book, and I'm sure I have it in on Blackboard. Let me see if I can't find it. Chi-square table. Here we go. I think that's it. Nope, that's not it. I'm pretty sure I posted one. Come on. Help me out here. Chi-square. Well, I'll tell you what. I'm going to blow this up because I have a chi-square table on here. Okay, here's what our chi-square value table looks like. Okay, in our case, we're talking about 1 degree of freedom, so we're dealing with this top row. And we're dealing the area to the right of critical value, the area to the right of the critical value is that we're willing to accept is 5%. If we want to be more certain that we can reject the null hypothesis, if we want to have less chance of being wrong, we might say that we want our alpha, our chance of being wrong, to be 1%, and we would use this. We would go all the way over to this column for our critical chi-square value. But we're generally going to be looking for an alpha error, chance of being wrong if we reject our null hypothesis, just like before, of 5%. Okay, so now let's go across here, and our critical value is 3.841. Okay, if we wanted to be 99% certain, an alpha of 0.01, our critical value would be 6.6. So let's go back to our calculation. Our calculation of chi-square was 4.16. Our critical value at 5%, alpha equals 5%, is 3.841. Can I reject my null hypothesis? Anybody want to guess if we can reject the null hypothesis? Yeah, we can, because our calculated value of chi-square exceeds our critical chi-square value that we need to be 95% certain or have less than 5% chance of being wrong if we reject our null hypothesis. Okay, so now let me ask you something. Can we reject our null hypothesis at 99% certainty? In other words, alpha is equal to 0.01. We want to get far enough out there that we're only 1%. We can't, because we would have a critical value of 6.6 instead of 3.84. Very good. I'm going to go. Somebody asked me to go back over the interpretation of that graph. I want to emphasize that I want you to understand the graph, but the real critical thing you got to hang on to here is that you have to know when to reject your null hypothesis. Okay, and that's given to you by your chi-square table and your degrees of freedom. Had this been a 2x3 table, that would have been 1 times 2 is 2 degrees of freedom, and our critical value would have been, even at 5%, would have been 5.9, and we wouldn't have rejected our null hypothesis. So it's not just a single curve, it's a curve for each degree of freedom. It's a different number that represents that 5% chance of being wrong. Okay, but I'm going to go back to that in a second. So we have 3 critical tools for analyzing categorical variables. One of them is relative risk, one of them is odds ratio, and the other one is chi-square. When we're dealing with relative risk and odds ratio, we determine whether or not we can reject the null hypothesis, that there's no association between those variables. We determine that by looking at our confidence interval and making sure our odds ratio or relative risk, a confidence interval for the relative risk and odds ratio, does not include 1, which would mean that it's the same risk. And with chi-square, we do something that's a bit more similar to the t-test. We actually look up a critical value, which will tell us whether or not the differences between our observed values and our expected values are different enough that we can say that we don't have an issue with rejecting the null hypothesis at the level of certainty that we want. Okay, so we have those 2 tools now. Let me just go back over. I want to go back to that chart, to that table. The way that graph works, if I can find it again, it's not here, it's not there. Did I close it? Nope, that's not it. Okay, let me go back here. We'll reopen it here.